Good afternoon, everyone. Hope you have a nice weekend. And today is Monday, right? So we need to work together to learn something. So let's recap what we have learned last week. The first topic we learned is homogeneity, right? Dimensional homogeneity. So you need to know the dimension on the left-hand side will be equal to the dimension on the right-hand side. And then after that, we learn dimensional quantities, like the one I mark here, which is in yellow color, like x is the power x, right? And the exponential x, and sine x, log x. These are all dimensional quantities. So according to dimensional quantity, you are able to find out some unknown symbols, the unit of the unknown symbols. That's what we need to learn. And also you will know that the physical meaning of the unknown symbols, right? Okay? So this is important. And then for the summary, I'm sure you all already know the scientific notation, significant figures, and precision. So you need to know the scientific figures, how to do addition, subtraction, multiplication, and division. Okay? Right, so I just want to let you know that please don't talk in the classroom. Otherwise, I will invite you to leave this classroom. Okay, please don't chat. Right, so the sample variance of scattering data, for example, if you have 10 data, which is the same data, made by the same experiment. So you will have initial data, which is xi, right? And range, which is the maximum, minimum. And then you need to know the average of these 10 data, okay? So in order to find out these 10 data are good or not, so you have sample variance or standard deviation to quantitatively verify these 10 data. They are from the very good experiment, or the data is scattered very widely, which is not can be represented as a kind of one data. So as a result, you will get something like this, which is x, right? Which is x equal to x mean minus plus error limit. The error limit can be range. Okay, can be standard deviation. Normally, we use standard deviation to represent the error limit. It can be 1 standard deviation, 2 standard deviation, 3 standard deviation, or even 4 standard deviation. It all depends on what's your definition. Okay, right. And then in the end is dimensional homogeneity, dimensionless quantities. Right. Okay. So in the section 2.7, we start from how to fit in a straight line. You have 10 data, right? These 10 data are not from the same experiment; they are from the different experiments. But these 10 data are linear, so we need to find out the equation to represent these 10 data. Okay, so these 10 data can be represented by an equation, which is a mathematical model. And you know that this linear equation is very easy, because this will be something like y equal to ax plus b. And the thing is, you need to find out a and b, right? So in the section 2.7c, fitting a nonlinear data, once you have 10 data, they are not linear. So you cannot use y equal to ax plus b to represent these 10 data. So what can you do to make it become a linear, right? The most easy way to make it is to make it become a linear. So you will become quantity 1, and x will become quantity 2. So this is the example to show you that the fitting nonlinear data from y equal to reciprocal of x plus of a plus b. So if you have quantity 1, which is y, and this will be quantity 1, which is y. And this is quantity 2, you will change to x to become reciprocal of x. Okay? So make it become linear and then do it as a linear. Use the linear method to do it. So once you have 10 data, how can we do it? Once you have 10 data, how can we do it? Let me show you. Okay, so any have we been here before? Yes. Right. So this is the one I showed you last week. So here is that also I think I have shown you here before, have I? Oh yes, I think I did. So the point is that, okay, we learned this. This is the one I want to recap today, and which is important. So there are some common nonlinear function, and you can make it become a linear equation. So this is the one I just showed you, right? The reciprocal of x. And then this is also important, which is power, and this is exponential function. So if you have an exponential function, you to use natural log to represent, and then you can use it as a y because you use this, right? So you have log y and natural log a plus natural log b times x. So the quantity 1 will change from y to natural log y. The quantity 2 here, this is quantity 2. Quantity 1 here, you will change from the x to become x. There's no change. Right. So this is a exponential function, and this one is power law. So you understand from this side, this will be natural log, right? And this is will be the normal one. So for the y is, if you have a power law and you times natural log in both sides, you will get natural log x equal to natural log a plus b times natural log x. So as a result, you'll find out that y-axis change from y to natural log y. X-axis you'll change from x and to become natural log x. Right. So this is fitting nonlinear data. We learned this on last week. You know that if you have 7 data, which is from you have x and y from 1 to 7, and this is 1 from 49. And if you plot in the figures x and y, you will get a curve like this. And then if I told you this 7 set of data follow the power law. The power law is y equal to a times xb. Or remember, this might be in your final midterm exam. Okay, midterm exam. So please remember, if I say power law, you need to understand power law is y equal to a times x power b. Okay, this is called power law. Okay, so if I tell you that this 7 set of the data obey the power law, then you understand this. You can put this number in here, and you can get x here, you can get y. So as long as you find out a and b here. Okay? So if you know that this is power law, you times natural log x, natural log on both sides, so you got natural log y equal to natural log a plus b times natural log x. So let's use this as a natural log x, natural log y here. So if you have natural log x, you got these numbers, right? You change from x to natural log x. You change from y to natural log y. So again, if you plot natural log x versus natural log y line, you will get something like this. So as I just told you, quantity 1 change from natural log change to natural log y, quantity 2 change to the natural log x. So you get something like this, the 7 set of the data, you got this. And the good thing is you realize this is a straight line. So if this is a straight line, and you can easily find out A and B. How? How? I told you before, right? I told you before. You can find out 2 points. If this is a straight line, assume these 7 sets of data are good. So you just find out randomly 2 data, and you get a straight line. You find out A and B. Or you just plot by a ruler. Okay, you have reciprocal and you have a slope. You can realize A and B. Okay, method 2. Method 1, if we follow the textbook tells us, method 1 is if you have a ruler and just plot by yourself, follow your heart. Okay, and you got reciprocal, you got the intercept, you got a slope, and you can realize A and B. Method 2, you point out you have 2 points, and then you find out A and B. Method 3, which is a more scientific method, we call it statistic technique. You can have linear regression, square root to find out this, to use this statistics technique to find out A and B, which is more scientific way. Okay, but anyway, this is an easy way. My suggestion is you just get 2 points and get a straight line. Okay, so this is called fitting nonlinear data from to linear data. So do you have any? So the trouble thing for this method is you need to change from x to natural x and then get something like get these numbers. Right? So it's troublesome. You waste it takes your time. And the good thing for the engineer is you want to make something complicated to become simple. Okay, this is the job for the engineers, as you are the student in the engineering college. Right? So you might think, well, Professor, this is very troublesome. You have 50 data, then I have to change from 50. I have changed to 50. I have changed 50 data to become natural X or natural Y. Of course, now you use Excel, it's easy. But is any other easy way to do this? Yes. That's what we are going to talk about this. But before we talk about the new topic, let me summarize the section 2.7c, the fitting nonlinear data. Important thing is you change it to, if it's nonlinear data, you change to linear equation, linear line to make it to become linear, to make it become a linear equation, right? Right. So the section 2.7d is called log coordinates, logarithmic coordinates. Have you learned this before when you are a high school student? You don't know? Well, I think you have learned, but you probably don't know this. This is a kind of comparison. This is rectangular paper. So as you know that from 0 to 10, you have the same distance from 1 to 2 to 3 to 4 to 5 to 7, right? So this is 10, 20, 30, 10, 20, 30, 40. This is called rectangular paper. But on the other hand, you have a log paper, which is this is a rectangular scale, right? Rectangular scale, and this is a logarithmic scale, or you can call log scale. Log scale is that from this is 1, and this is 2, 3, 4. As you can see, the distance between 1 to 2 and distance between 2 to 3 are different, right? Because this is log scale. Because you use this point to become log. So you have this from 1 to 100, this is from 1 to 1000. As you can see, this is the same length, right? So this scale can make it very big. From here to here is 30 only, from here to here is 100. From here to here is 1000, here to here is 40 only. So the good thing for the log paper or log scale is that, for example, you have a data like here, something like this, which is 2, 800. If you want to plug in this rectangular scale, 800 is very far from the bottom to the top. So this paper is not good enough. So if you want to compare 2 to 2 and 2 to 800, this paper is not suitable. But for this paper, this is good. Okay? So let's go back to the question we learned just now, is that this log coordinates, originally you have these this 7 set of data, right? So this 1 to 7, 1 to 49, and we understand already this is follow the power law. So the power law tells us that you change from the x to natural log x, y to natural log y. You got the data, a set of 7 set of data here, and then according to this data, you plug something like this, and you realize this is linear. So you can get these 2 data, which you can point out 2 set of data, for example, like this one, this set, and this set, and you put it into this equation, you got the A and B. Okay? And you realize you can predict where is the 1.2 and related to this number. Okay? This kind of prediction mathematical model to do the prediction of the data. Right, so this is method 1. So as I just told you, is any other way? If you have a log plot, this is log plot. As you know, if you have a log plot paper, you don't need to change x to the natural log x. You don't need to change y to the natural log y. If you have this number and you plug into this log plot, if you have these 7 set of data and put it into the log plot, you also get a straight line. These 2 represent the same thing. You just change the coordinates only from rectangular coordinates to become log coordinates. Okay? So this is x, this is natural log x. This is y, this is natural log y. So you don't need to transfer to this natural log x and y, you can get a straight line. Bingo. You realize, wow, Professor, this 7 set of data follow the power law. This one. And again, you pick up 2 points, you put it to this, you got the answer. Okay? Right. So, the important thing for this is to be an easy way to change to the rectangular coordinates to become log coordinates, right? Rectangular coordinates become log coordinates. Okay, so as I just told you, this 7 set of the data doesn't change the numbers or anything. You just put into the different coordinates, it tells you the same thing. Right, so this is called log plot. Log plot, right? This is log plot. And another one is called semi-log plot. So log plot is for the power law, but semi-log plot follow the exponential function. Hope you still remember. So this is power law. Again, we just realized log plot here. And you realize this is the equation to represent this log plot. How about exponential function? Exponential function follow the natural semi-log plot. So you times natural log on the both sides, left hand side and right hand side, you got this equation. And you realize y-axis change from y to quantity 1 change to from y to natural log y. Quantity 2 doesn't change because it is x, right? So you got something semi-log plot. So you know that this rectangular coordinates, right? And this is log scale. So if you have a straight line, something like this, bingo, you realize, wow, Professor, I can make a mathematical equation to represent this line, which is exponential function or exponential equation. Okay? Any questions? No? Okay. You are welcome to come to me after lecture in Mandarin. Right. So there are some additional informations. If the plot appears linear semi-log plot or log plot, how to find A and B? How to find A and B? You follow the same way. First, if you have a straight line, my advice is pick up two set of numbers, right? Two set of numbers, 2 points, and then you put these 2 points into this equation. You got A and B. Okay. And how about semi-log plot? You will have this, right? Again, you pick up 2 points. You got a number. Okay. This is an example to let you have exercise. I don't want to waste your time. So please go home and do practice by yourself. Okay? Or if this is not clear, I mean, there's no, the description of the example. You go to library to get, to get these sentences. Okay? Or you find your senior if he has a book, if he or she has a book. Okay? So practice this, and then I'm sure you will get good score in your midterm exam. By the way, I hate to say exam. I always say celebration of learning. It's very good to learn something and you practice and you get points. It's very exciting things, right? So we do the celebration of learning. In your midterm celebration of learning. Celebration of learning in the midterm time period. Okay? Right, so this is the conclusion for your information. Right, so I want to show you some of the log plot or semi-log plot in the real life. This is the, can you tell me this semi-log plot or log plot? Can you? I'm sorry, it's here, semi-log plot. Semi-log plot this is a rectangular scale, right? And this is log scale. So this follow what? Exponential function or power law? Exponential function, right? So you understand, if this is a straight line, you can write down a mathematical model. Okay, so what is this for? This is called volcano. Sabatier principle volcano plot. It looks like a volcano. The things got the material which on the top, which is a very good material. For what? For fuel cell. Okay, this is a kind of material we regard this as a catalyst. What is catalyst? Catalyst is that catalyst doesn't involve any reaction, but it helps reaction to reduce the activity energy, so you can accelerate or you can reduce the activity. It can make the reaction occur easier, or it can make the reaction take place easier. Okay? So this is catalyst. So as long as you find out this is the, if you find out something like this in the top, everybody try to go to the top. And then once you find out, you might get Nobel Prize. Okay, it's kind of holy grail in the field of catalyst. Right, so this is another example is log plot. This is log plot. This tell you that this is power density. I don't know. I forgot to tell you. This is the oxygen absorption energy on the catalyst. So your oxygen attached on the catalyst. Energy required. This is the scale. Okay, and this is reactive OR. This oxygen reduction reaction activities. So if you have, as you can see, the absorption energy cannot be too small, cannot be too big. You need to have a right energy so that you can get a very good activity, reaction activity. And this reaction activity related to the oxygen absorption energy is not linear. It's a kind of power law. It's kind of exponential function. So if you increase a little bit, absorption energy increasing a little bit, it increases the activity increased dramatically, very large. So this is a big scale, right? So you increase a little bit, and then energy activity increases very large, very big. Okay, that's why we need to use semi-log plot. Okay, so this is another example of the log-log plot. As you can see, this is called power density. This is called energy density. It's related to with something related to the battery. Again, this is the best. As long as you have something, the battery is reached to this region, which is a very good power density, very good energy density, and which is good. This is the best energy. Oh, sorry, the best battery. And this is called random plot, log-log plot, random plot. Okay, finally, I want to show you that this is the abundance of the elements in Earth's crust. Earth's crust is that if we know that if we use silicon as the base, this is the abundance atoms of the element of per 10 to the power 6 atoms of the silicon. So silicon is here, which is 10 to 6, okay, atoms. If you use this as a standard, you understand oxygen is more than silicon, and alumina is less than silicon. Okay, so this is what this is. This is what this is semi-log plot. This is atomic number from 1, 2, 3, 4, 5, 6 to 90. This is the atomic number, and this is scale. So as you can see, if you increase 1, and then you can drop very huge. For example, this is rare earth or precious metal. Okay, it's all located here, which is 10 to minus 3, and this is 10 to power 10 to 6, which is very, very, very different. Okay, so this atomic number, this is the abundances. So I want to ask you a question. Does anybody tell me what's wrong with these figures? What's wrong with these figures? Anybody want to tell me? 1 point. I will appreciate your answer if your answer is correct. And this is very important. You don't want to make this mistake after 4 years of the chemical engineering study. Does anybody want to tell me what's wrong with there's only one mistake. Actually, it's from Wiki. Okay? And anybody want to tell me why professional professor will say this is not a correct figure? It's one mistake. And very fundamental mistake. Anybody want to tell me? 1 point. I'll be very happy and I will appreciate your answer if you got the answer right. Anyone? Anybody? No? 2 points. I think Google might not be able to tell you this. I don't want to go to 3. It's too heavy for me. Too heavy for you too. Right, let me tell you the answer. You know, if you want to make a line, that means from the end point to the start point, it needs to be a continuous. Right? For example, if you have a line from 7.5 to 7.8, this is the line. So the line 7.5 to 7.8, they must have a 7.7 or 7.6 or 7.61 or 7.6125. So you can make this line continue. But if 2 points there's nothing, can you make a line? Can you? No, you cannot, because this is not continuous. This is not a continuous straight line. So when you think of this atomic number from 1 helium, right? Hydrogen, lithium, lithium 3, right? Helium 2, barium, boron, carbon, nitrogen. So they make a line together. That means there's something between lithium and barium. Can you find lithium, something between lithium and barium? If you find, please tell me. We can get Nobel Prize together. But as a matter of fact, you cannot make the line like this, because this is nothing between number 4 to number 5. There's nothing between number 5 to number 6. So you cannot make a straight line like this. Okay? So what can you do? What can you do? If you cannot make a straight line, what can you do? Bar chart, right? You use bar. You know? Do you know why it's bar chart? No? Okay, good. Somebody can tell me. He understands. Okay, good. Anyway, this is out of scope of our lecture, but just want to tell you some principle knowledge so you don't want to make the same mistake. Right, so now we go to the end of the 2.7 E, which is E, fitting a line to a scattering data. As I just told you, if you have a ruler, you make a straight line. If you realize this is a straight line, you pick up 2 sets of points, and then you put these numbers into your equation. Or you use a more scientific method, which is linear regression or method of the least square. These are all mathematical equations you can find out, or if you have a smart calculator, you can get this. You can get the answer. Okay, so I finished this section. So before we move to the Chapter 3， 我最不喜欢2件事，第一个是欺骗，一个是作弊，一个是作弊，一个是在课堂上讲话聊天，这2个是我最不喜欢的。如果你踏到我的底线，那我就会很严厉的处罚了。如果你要讲话没有关系，你到外面讲话，讲完话再回来。可是呢，你在这边讲话的话呢，很多同学都想要听我上课啊，对不对？你就影响到别人，你也影响到我。如果你影响到我呢，你就要出去了。OK， right。Right, so now let's go to the chapter 3, processes and the process variables. So what is process? So as we know that we learned this in the chapter 2, process is the most important topic we need to learn as a chemical engineer in your college. So the process unit, you have input. When you have input, you have physical change and physical change. So, and after this change, this change can be a reaction, can be a filtration, can be evaporation, can be a heat exchange. These top 3 is kind of mass change, but this is energy change. Okay, so when you move out, you got products. So this is a process. This is a process. But if you put process together to become processes, so you will have every process. You will have input and output. So for example, this process A, you have input A and output A. But for process B, the output A can be, or in this case, is input B. And so the process B can only have 1 output. It also maybe can have 2 outputs or 3 outputs. So the process stream in process unit B are the input B and the output B1 and B2. So output B1 can be input C, right? In this case, right? So what's the role of the chemical engineering in the processes? As a chemical engineering, you need to do the design of this process. Okay, and after design, you need to do the operation. And once you complete operation, the technician will take over your job. So he can do the daily operation. But in the very beginning, that's your job because you design the machine, you design the process. Okay, so what's the design? The design is that this is kind of design. You don't really build the reactor. You don't really build the separator. You just have a piece of paper and pen. You draw the flow chart. This is what we call flow sheet. Okay, as you remember, this is kind of flow sheet. This is one process, process B, process C, process D, for example. Okay, and then not only draw the process, but also you need to specify each process. For example, you need to find out, is this a reactor? And then you specify the separation equipment, which is chemical physicals. Or this is energy exchange. Okay, heat exchanger. And then you need to worry, you need to realize not only in this, but you need to realize what's the temperature inside, how to increase the pressure, and then what's the flow rate, what's the fit, what's the material you need to fit into this reactor. Okay, so once you finish the design, and you need to start to build up the machine. Okay, you need to make it work. And then not only to make it work, but because you are running a industry or you are running a factory, so you need to reduce the input, increase the output, or increase the reactivity, increase the conversion rate to use less raw material and to use less raw material and energy and make a good products, right? And then also, if something went wrong, okay, you need to do the troubleshooting. So because you are the one who know this machine well, you are the one who design. Okay, so you need to do this. And also, during the daily production, you have something, product demands. You need to realize, you need to find out how to increase the productivity, right? Or once you have a bottlenecking, okay, this is called the bottlenecking. Also, one is in the economic crisis, you need to reduce the production in an economic way. So how can you do that? So this is one of the examples I hope you still remember. You need to have a factory and you go to the QA, and QA will show you that QA will show you, right, this rejection and this accept. The 500, for example, you can accept a lot of benches, and then there are some bad bench will reject it because the quality is not good, and you want to do the maintenance or you want to continue to do the production. And this question show up in the chapter 2. I hope you remember that. So this chapter 3, is a very simple chapter, again, like chapter 2. So the definition of variables, like how to define the mass, volume related to the density, and the pressure, how to define the pressure and temperature, and how to measure the pressure, how to measure the temperature, and how to measure the flow rate. Remember the flow rate? Okay, does anybody want to tell me what kind of instrument we use to measure the flow rate in English? Anybody want to tell me? 0.5 point. How do you measure the flow rate? I told you in the chapter 2. Yes? Okay, good. Right. I expect you to talk to me in English, but anyway, thank you. That's good. That's good. Right, because we are going to talk about 负质流量计 in this chapter 2. Okay? Right. So first one is section 3.1, mass and volume. You understand this, right? So for density is mass divided by volume. You understand this. So you can SI system, CGS system, the American engineering system. So another term is specific value. What is specific value? Specific value is that the value divided by unit mass, right? Unit mass. So the specific value is value divided by unit mass, and then this is what? The reciprocal density. Reciprocal density. Okay. And this is very easy. You know, if you have mass, you know the density, how do you find out the value? Or if you have value, you have density, how do you find out the density, mass? Okay, so this is very easy. So the point here is that, what is this? Dimensional equation, right? What is this? Conversion factor, right? So what you need to learn from, you need to apply what you learned from the chapter 2 to the chapter 3. So this is the key you want to know. Okay, so conversion factor, dimensional equation. How about specific gravity? Specific gravity is density divided by density of references. Okay, reference normally is water. Okay, so I want to skip this because this is very easy. You can read this by yourself. So this is no problem. I think I better skip this, easy. So the important thing for you to understand is that, you know, dimensional equation, conversion factor is density. Okay, if you want to change from value to the mass, or you want to change mass to the value, the conversion factor is density. That's the key. And the second topic here is that once you change the temperature, the value will change. Of course, the mass doesn't change, but value will change. So, in terms of liquid, this is for some of the liquid, this is the equation you need to know, but I don't want you to remember this equation because, you know, this is the initial value, this is the final value. And related to what? Related to the temperature. And alpha, beta, gamma is a kind of parameter. It depends on different liquid. Okay? So this is a kind of coefficient. You have different numbers for different liquid. Okay, you don't need to remember this, but you realize what? Temperature increase, value increase. Okay? And this is example show you the mercury. Mercury is the alpha, beta, gamma. Alpha is here, beta is here, and truncate this. You omit this gamma. So, and how about liquid? How about solid? It's rather simple. Is that again, if you change the temperature, T is the differences of the temperature from temperature 1 to temperature 2, right? And C is a coefficient again. So you have a value 2 and value 1. It's easy. Right, so I just want to skip this. You can do this practice by yourself, of course. So, this section has 3 topics. One is that the density tell you this is a conversion factor, okay? And then you also learn the specific value and the specific gravity. And thermal expansion, which is increased temperature, and then the value increase. What happened to the density? Density decrease, right? Right. So the topic 2 is flow rate. And this will be in your midterm exam, okay? So please remember this. I want you to know how to, as a chemical engineer, how to measure the flow rate. And the thing is that you need to know what's the mass flow rate and volumetric flow rate. So let's start from a very simple concepts. If you have a ball or baseball, you throw the baseball from A place to B, and you know this is kind of speed, right? You want to know the speed. And this is a kind of movement. So you call this velocity or speed. So it's the length divided by time. So you know the speed. This is an object, okay, a solid object. How about water? How about the air? How do you define the speed of the water or the speed of the air? This is what we call fluid. Okay, fluid. Liquid and gas are all regarded as fluid. Okay, because it's not like a simple object. So we call it flow rate. We call it flow rate. We don't call velocity or speed, because when you call velocity or speed, we are regarding this as a kind of object. Okay, and then there are two flow rates. One is mass flow rate. You count by mass. Okay, and second is you count by volume of the fluid, volume of water, volume of air, for example. So this is important. This is a kind of concept today. You know, if you have a if you have a water pipe and you have a tap here, you open the tap and water starts to flow, right? Okay, so if you open the tap and then you count 1 second, 2 seconds, 3 seconds, 4 seconds until 5, and you have amount of water, and you measure the amount of water. I mean, it can be mass or can be volume. So, and divided by time. So this is what? If you have a mass, you count by mass, you divide it by time. This is what? Mass flow rate. If you count by the volume and divide it by time, this is volumetric flow rate. Okay? So this is very easy. Okay, flow rate. And then how do you use a symbol to represent flow rate? Very easy. This is M represent mass. There's an over dot here. If you have a mass over dot, that means what? Mass divided by time. That means what? That means flow rate. Mass flow rate. If you have volume over dot, that means volumetric flow rate. Okay? So M is mass, V is volume. So now you learn mass flow rate and volumetric flow rate. Okay, so if you this is if you have the scale here like 500 milliliter, 1000 1000 milliliter, 1500 milliliter. So you can measure the volume, right? So if you don't have a balance, and you measure the volumetric flow rate, how can you change the volumetric flow rate to mass flow rate? If I tell you, if you don't have a balance, how can you change this volumetric flow rate to mass flow rate? Density, right? Because regardless of the second here, how can you change mass to the volume? How do you change the volume to the mass? By density. Because for the mass flow rate and the volumetric flow rate, both of them have the second. Yeah, but you omit the second. So the easy way to get volumetric flow rate from the mass flow rate is using conversion factor, which is density. It can be water, right? It can be air. If you know the density of air, if you know the density of the water, or even if you know the density of the methanol, okay, or alcohol, right? So this is the one I want to show you. Is density equal to the mass divided by volume, and also equal to the volumetric flow rate divided by is also equal to the mass flow rate divided by volumetric flow rate, which is M over dot divided by V over dot. Okay. So how do you do the measurement? How do you do the measurement? Remember this? And I want you to remember this because this is important, and this will be in your midterm exam. So the rotameter, there are a few important information you need to address in your midterm exam paper. So rotameter is a device that measures the flow rate of a liquid or a gas in a closed tube. I want to ask you, this measure volume or this measure mass? Excuse me. Anybody want to tell me? Remember when we talk about this in chapter 2? Please tell me this is the measurement of the volumetric flow rate or mass flow rate. Which one? Remember the calibration? Barbara, I show you here. Remember? 0.5 point. I want you to raise your hand. You lose nothing. You have nothing to lose. Even you get wrong answer. Right? So the air go in or water go in from the bottom and go to the top and do the measurement. And remember I show you Barbara. I also show you a video. And they measure mass or it measure mass or it measure the volume. So it's yes. Volume, right? So it's volumetric flow rate. Okay, good. So this rotameter is an equipment, a device to measure the volumetric flow rate. So once you measure the volumetric flow rate, I want to tell you, I want to know mass flow rate. How can you do that? As long as you know the density of this fluid, it can be water or can be air. So you can convert volumetric flow rate to mass flow rate. Okay? So rotameter is a device that measures the flow rate of the liquid or gas in a closed tube. This is a closed tube. Okay, this is a tube. Okay, it belongs a class of the meter called variable area meter. This is variable area meter. It's a kind of tapped, T-A-P-E, tapped, T-A-P-E-D, tapped tube, okay, which measure the flow rate by allowing the cross-section area of the fluid travel through a very causing some measurement effect. So important thing is this is from large area to small area, and the float will stop in somewhere in the middle. And then because it stopped somewhere in the middle, that means it got balanced. So the drag flow upward force will equal to the downward force, which is the force of the gravity. If you stay here, you get a reading. So you know the flow rate. Okay? Right. So the rotameter the float is like this. So you have something that taper the vertical tube, from the wide to the small, and the fluid in, and fluid out, and you got float goes up, right? And then you have float out, right? And this is reading. So once you have reading here, you understand it should be somewhere in the middle, right? So if you increase the flow rate, this float will go up, or will go up, right? Will go up. And this is to the measurement of the volumetric flow rate. Okay? Well, I encourage you to visit YouTube. So if you type rotameter, you'll get a lot of information if you still don't understand. But what I want to tell you is that in your midterm exam, I want you to show me this page. Okay, the page 34 and the page 33. I want you to tell me what you know about the rotameter. Okay? Important thing for you is to get the key word. Okay. So the method 2 is called orifice meter. Orifice meter is that we also call it a manometer. Manometer. So it's different. You have different fluids, right? The fluid 1 and fluid 2, and you can have this kind of equation. I'm sure you learned this in your college, in your high school. So you want to relate because the pressure will be different from A place to B place. So you got delta P and you got a different value. So according to this, you can get the flow rate. Why? Value divided by time is flow rate. Okay, so but A is for rotameter is more practical. So I want you to know the rotameter better than orifice meter. Right. So this is the summary: the volumetric flow rate, mass flow rate, and conversion, and flow rate measurement. Okay. So so let's go to chapter section 3.3. So section 3.3 is that in the liquid or fluids, you need to know the chemical composition. Okay, how do you define the chemical composition? For example, you have 5 species, A, B, C, D, E, 5 species, and you put these 5 species into a container and become a mixture. And how can you present these 5 species in concentration or composition? So first of all, we need to know the moles and molecular weight. And this is easy, so I'm sure you understand this, so I will skip this very quick. So molecular weight is what? Molecular weight is, you know the molecular weight, right? So mole, what's the mole? Mole is 1 mole equal to 6.08 times 10 to the power 32 molecules or atoms. It's called 1 mole. Okay? Right, so this carbon monoxide molecular weight, you understand, you plus carbon and oxygen, you become 28. This is what we call the molecular weight, right? Okay, easy. If you understand, the Avogadro number is 6.02 times 10 to the power 23 molecules or atoms. It's called 1 mole. It's easy. Right, so please practice this by yourself. This is not difficult at all. Right, so this is important. This is the things that I hope you still remember. If I want you to convert volumetric flow rate to the mass flow rate, the conversion factor is what? The conversion factor is density, right? So if I want you to convert mass flow rate to molar flow rate, how can you do that? If you only have one machine, an instrument or device, which is the measurement of volumetric flow rate, and I want you to change, I want to know, I don't want to know mass flow rate, I want to know molar flow rate. How can you do that? Easy, right? You have time here. So from the volume to the mass, the conversion factor is density. To the mass of the volume, the conversion factor is what? Molecular weight. If this is a pure material, it can be molecular weight or atomic weight, right? Or if it is a kind of combination, you just use the average molecular weight or average atomic weight, right? Okay, so conversion factor is molecular weight. Easy. So please don't forget about this. The concept here is the rate only. So I'm sure you understand how to convert mass to the molar moles, right? Right. So there are some easy practice. Please do this by yourself, and don't forget about conversion factor, dimensional equation and conversion factor. Okay, this is conversion factor. This is dimensional equation. Right. So the key, the summary of the section 3.3. Right. So now the section 3.3 tells us that if we have a combination of 5 species in a mixture, so how can we identify the mass fraction, mole fraction, and average molecular weight? I'm sure you learned this when you are in high school, so just do this quick. Mass fraction, easy, right? Mole fraction, you have all the moles in the, you have mole A divided by total moles. You have mass A divided by total mass. It's easy. How do you do the conversion? Again, conversional factor and the dimensional equation. Okay? So this is easy. I don't want to waste your time. So do some practice by yourself, easy. Okay, so how about average molecular weight? Average molecular weight is you have fraction, molar fraction. Molar fraction A times molecular weight of A, right? Plus molar fraction B times molecular weight of B. Okay, you got M over bar. This is called average. M over bar. Okay. How about if you don't know the molar fraction, you just know the mass fraction? Again, the conversion factor is what? Is atomic weight or molecular weight. So if you do a simple calculation, you will get reciprocal of the average molecular weight will equal to this equation. And this is not difficult. You can divide this by yourself. Okay? So please do this. So this is one of the classic example is that the molar composition of nitrogen and oxygen in the air is about 79% for the nitrogen and 21% for the oxygen. And when we talk about 79 and 21, this is this is a molar composition. This is not the mass composition. So if you want to change from molar composition to the mass composition, it turned out to become like nitrogen 76.7, oxygen is 23.3. Okay. So this is the important things I think you need to know. Don't mix up 79%, 21%. This is more composition, not mass composition. Okay, let me go through this quick. So this is kind of the term for the concentration. When you do the definition of the concentration, the fraction and concentration and composition. Normally, composition is a kind of sum to address the portions. It can be fraction, it can be concentration. Okay, so mass fraction of A, you understand, right? Mass A divided by total mass. The volumetric fraction of A is value A divided by what? Total mass of volume, total volume. So how about mass concentration of A? Mass concentration of A, when you do this is mass A divided by volume. Remember this. If we talk about concentration, it's always divided by volume. Okay? The molar concentration of A is what? The mole divided by volume. Okay, so this kind of definition, don't mix up, don't get confused. But you don't need to remember this. So once when you are working or when you do confusing, you just Google it, and this will show up. I just want to tell you, when you talk about concentration, it's always divided by volume. Okay, how about molality? M, we use this a lot, right? Molality, which is gram mole per what? Per liter. This is molality, which is the most common used, right? When you are in a chemistry lab or chemistry laboratory. Okay, so this is definition of concentration. Please realize this. So the molality, I just show you here, is easy, so I don't want to waste your time. So please do this. So important thing is what? Conversion. You need to have a conversion factor. So final topic of this is part per million and part per billion. We use ppm and ppb. So what is ppm and ppb? So once we want to know the very small composition, amount of composition in a big tank, so we use this part per million is 10 to 6. Okay, And this might be in your making exam, please remember this ppm is part per million. So this part, 1 part of the million. Okay? And ppb is part per billion. Billion is 10 to the power 9. So y is what? Yi is a fraction of components in the solution. So once you say this is a fraction, that means what? That means this is a dimensionless quantity. Okay? So there's no dimension. It's a dimensionless quantity. So this is a dimensionless quantity. I want to show you an example here. For a liquid, you know, ppm and ppb, normally we use mass ratio. Remember, this is ratio. Once we say ratio, this is a dimensionless quantity. So it can be 1 out of 10 to 6 kilogram. Okay, and this is dimensionless quantity. Why? Because you can easily to measure the weight of the liquid. But is it easy to measure the weight of the gas? No, it's not. We use more. We use more. So more ratios usually. Okay, and remember, important thing is that ppm, ppb is a dimension. They are all dimensionless quantities. I want to give you an example. The power station, air near the power station contains some of the pollutions. One of the bad pollution is sulfur oxide. Why? Because if you have power station use coal has a sulfur in the core. So once you burn the coal, the sulfur will become sulfur oxide and release to the air. And once the sulfur oxide released to the air and you get water, it becomes sulfuric acid, which is not good. We call acid rain, right? Acid rain. But anyway, so for example, if the air near the power station has a 15 ppm sulfur oxide, what does that mean? It means 15 gram per 10 to 6 or 15 moles per 10 to 6 mole. Which one? Of course, we talk about, because sulfur oxide is a gas, right? Sulfur oxide is a gas, so we use more instead of weight. Okay, and dimensionless. So in terms of Mandarin, this is 每百万沫的空气中含有数沫的二氧化硫。Okay, so if you remove more, that's dimensionless quantity. Okay, I think I finished the topic today. So, do you have any question for me? No, so good. So I hope you enjoyed the lecture today. And before you go, and please